In this video, we are going to look at section 6.4, working with Taylor series. So we're going to use the Taylor series to derive other functions. But first, we're going to talk about the binomial series. And so with the binomial series, and this should be f of x is equal to 1 plus x raised to the r. For any real number r, well, let's first start with the way that we learned the binomial series back in pre-calculus 1, where we said let's look at r being only whole numbers, so 0, 1, 2, 3 on up. So 1 plus x to the 1 is 1, and 1 plus x to the 1 plus x raised to the 0 is 1. 1 plus x raised to the 1 is 1 plus x. And then we continue. Here's to the fourth power. Now, we know from either Pascal's triangle, if you prefer that, which is derived from the binomial theorem. Here's how we define the binomial theorem in our OpenStax Pre-Calculus book, section 11.6. We said if we have x plus y raised to the n, it is the summation of k equals 0 to n of n choose k, x raised to the n minus k, y to the k. So in other words, it looks like this, which is where we got the 1, the 4, the 6, the 4, and the 1. If we would have multiplied it out completely, we would have got this, or if we would use the binomial theorem, we would have also got this, or the Pascal's triangle, which is, of course, derived from here. Now, we are now going to look at it through the lens of Calculus 3, which says, let's start with coefficients of x to the n and the binomial expansion. So we have, just looking at the coefficients, the r choose n is r factorial, n minus r factorial. And then what ends up happening when I have f of x raised to the 1 plus x raised to the r, it's going to be r choose 0, r choose 1, r choose 2, all the way up until we've got r choose n of n factorial, because my 1 is just going to be powers of 1 here. If we use r equals 1 and we use this formula, we end up with 1 plus x to the fourth is 4 choose 0 times 1. 4 choose 1 times x. 4 choose 2 times 1. And of course, all the 1s are there. We're just not going to write those. And we can write this as 4 factorial over 0 factorial, 4 factorial times 1. 4 factorial over 1 factorial times 3 factorial times x, and etc. And we see that this is exactly what we had from up above. So then, if I want to expand this out for any value, any power of r, that's a real number, then what I may have is not a polynomial. I may not end up with a polynomial. So how do we do these when my r is, say, 1/2? Well, we use the Maclaurin series. And we evaluated it at x equals 0. So here's my f of x is equal to 1 plus x raised to the r. My first derivative, second derivative, all the way down. And then I evaluated at 0. Well, when x is 0, I have 1 raised to the 1. And then when x is 0, I have 1 raised to the r minus 1, which is still just 1 times r. And we get this, which means the coefficients of the binomial series now, when r is not a real number, or r is not a whole number, is going to be in this form. Any coefficient is going to be r minus 1, r minus 2, all the way up to r minus n plus 1 divided by n factorial. In general then, for us, when we are talking about non-real or non-whole numbers, they're still real numbers, non-whole numbers for r choose n is going to be in this form, where we have r minus 1, r minus 2, r minus n plus 1 divided by n factorial. Which means we now can write this without r being the power, has to be a whole number. So then we get this, which is the summation of n equals 0 to infinity of r choose n, x raised to the n is equal to this. We have r times x, or 1, r times x, r minus 1 divided by 2 factorial, and then times x raised to the 2. All the way down to where we get to some term that it's going to be r minus 1, r multiplied by r minus 1 plus 1 over n factorial raised to the n. At some point, we're going to have that. then we're going to continue because it's an infinite series. It doesn't stop there. It just continues. Now, we'd like to know where the radius of convergence is for this binomial series. So we start out with our ratio test, which is the rho is equal to the limit as n approaches infinity of a sub n plus 1 over a sub n. Now let's just focus in on the a sub n plus 1 over a sub n, and when we do that, we end up with r minus m over n plus 1 absolute values multiplied by x, the absolute value of x. Which means as n goes to infinity, because this power is n raised to the 1, and this is a power of n raised to the 1, we know that that part, the limit of that part is going to go to 1. So that means I'm really just looking at the absolute value of x. And the absolute value of x has to be less than 1 because we know that rho itself has to be less than 1 for it to converge, which means my radius of convergence is 1, and the interval of convergence is from -1 to 1. The endpoints that you are looking at, whether or not you include the -1 or not, and then you include the 1 or not, depends on the powers of r. So, if we look at for any r value greater than or equal to 0, the radius, the interval of convergence is inclusive of the endpoints. If r is between -1 and 0, not including 0, the radius of convergence includes the right endpoint. And if the r that we are looking at is a negative number less than 1, then we know that the radius of convergence is non-inclusive on either one of the ends. So now we are going to formally define the Maclaurin series for the use of finding 1 plus x raised to the r. This is going to be equal to the summation of n equals 0 to infinity of r choose n x raised to the n. So then we know that this is going to be equal to, if we were to expand this out, we would have 1 plus r times x, r minus 1 divided by 2 factorial x squared, and it would continue till we got to this number. And it actually would continue beyond that, but we can focus in on this number. So using that information, we were asked to find the Maclaurin series for this given binomial. So the first thing we notice is that it's not completely in the right form. The right form should be 1 plus, and we have 1 minus. So I want to write this as 1 plus a negative x raised to the 1/3. Now, using this theorem, then this is going to be 1, that's my first term, and then it's going to be plus r, which is 1/3 times x, which happens to be a negative x. Now, when I say this is, quote, x, in this is my, quote, x, okay? So that's going to be 1 plus 1/3 times negative x. That takes care of this term and this term. And then it's going to be plus my r, which is 1/3, my r, which is 1/3 minus 1, divided by 2 factorial, negative x, the quantity squared. And then my next term would be 1/3, 1/3 minus 1, 1/3 minus 2, 3 factorial, negative x raised to the 3rd power. Somewhere in there, I would have a term that is of the form 1/3, 1/3 minus 1, 1/3 minus 2, 1/3 minus n plus 1. All of this is going to be divided by n factorial, x raised to the n, and this continues. Now, the whole reason we're writing these out is so we can see the pattern recognition. Now, I'm going to come back over here, and so this is going to be equal to, I have 1 minus 1/3 x because of the negative. This ends up becoming plus 1/3 minus 2/3 over 2 factorial, and then negative x, the quantity squared, is going to give me a positive x squared. And then plus, I have 1/3, and then I have negative 2/3, and then I have the negative, let me see, negative 1 2/3 is 5/3. Is that right? Negative 5/3. So it's 3, 4, 5, 5/3. And then we have 3 factorial x to negative x. Let me bring that negative out front. So that's a negative because negative x to the third power is a negative x to the third. And it continues. So let me just rewrite this again so it makes it a little bit easier to see. So this is equal to 1 minus 1/3 x minus, because of this negative, is going to come out front. And this is going to be 1 times 2 over 3 squared times 2 factorial. And the reason it's 3 squared is because, now let me just come over here and show you why. I have 1/3 multiplied by negative 2/3. And then I'm dividing by 2 factorial, which is the same thing as 1/3 multiplied by negative 2/3 multiplied by 1 over 2 factorial. And that's why it is 3 squared in the denominator and 2 factorial multiplied by x squared. Now, this negative and this negative are going to cancel themselves out and become positive. And similarly, I'm going to end up with, so it's going to be minus 1 times 2 times 5 over 3 squared, 3 factorial, x raised to the third. Now, if I were to write the next term, which I don't have to, but I could, based on this pattern, it's going to be minus 1 times 2 times 7, or excuse me, 5, don't forget my 5 there, times 5 times 7, 3 raised to the fourth, 4 factorial x to the fourth. And so by looking at this pattern, we can determine what my Maclaurin series would look like. This looks like it's the summation of n equals 0 to infinity of negative 1 raised to the n. And then it's going to be 1/3 choose n x raised to the n. Now the reason it's a negative here is because of the fact this was a negative x to begin with. So it is negative 1 raised to the n, 1/3 choose n, so my r choose n, and then x raised to the n. And the reason we had to do that is because we had to figure out what was going on, whether or not I needed this negative 1 here, and we did indeed need that negative 1. Now let's take a look at our next example where I am looking at 1 minus x. And again, I'm going to write this as 1 minus or 1 plus a negative x. 1.01. Now I'm going to start writing these out again, just like I did before. So this is going to be equal to, and actually, you know what? Let me do this in blue so it's not going to be confused with what was above. So this is going to be equal to 1, because that's my first one, my first term, that is. And then I'm going to have plus 1.01 multiplied by negative x. And then I'm going to have plus 1.01, and then 0.01 over 2 factorial negative x, the quantity squared. My fourth term is going to be 1.01, 0.01, negative 0.99, 3 factorial negative x raised to the third. I'm just going to do one more term. So then plus 1.01, and then 0.01, negative 0.99, negative 1.99, 4 factorial, negative x to the fourth, and this continues. But you'll see the gist of it. So then this is equal to 1 plus, oh wait, it's a minus 1.01x. This negative is canceled out, so because it's a squared, so it's going to be plus 1.01, 2 factorial over, and then multiplied by x squared. And then plus, this negative is going to cancel with this negative, which gives me 1.01, 0.01, and then 0.99, 3 factorial, x raised to the third. This negative and this negative will cancel themselves out, and this is negative 1 raised to the fourth power, so that's also positive. So 1.01, 0.01, 0.99, 1.99, 4 factorial x to the fourth. And remember, this does continue. Now, I want to stop here because by just plugging and chugging when we first start, it doesn't follow the patterns that we had before. We had a 1, and notice on the previous one we had a 1, and then all the rest of the terms were negative. This is a 1, and the first term is negative after that, and then everything else is positive. This does not follow the way that we would expect it to be. So if it doesn't follow a pattern, it's not a clear pattern, then I'm going to go back up to here, and I'm going to look at, is there a way I can rearrange this so that I can get a nice clear pattern? And the answer is yes. What I'm going to do is I'm going to rearrange this. I'm going to move all of this over, move all of that over, and I'm going to rearrange, move all of that. I'm going to rearrange this as 1 plus x raised to the 1 plus 0.01. This then is 1 plus x raised to the 1, excuse me, these are minuses. These should be minuses. So minus and a minus. And then multiplied by 1 minus x raised to the 0.01. Now, 1 minus x raised to the 1 is just 1 minus x all day long. So that's not the part that I have to worry about when I want to write this out using my Maclaurin series. This is the part that I'm going to focus on. I'm going to see whether or not this is going to give me the pattern that I need. So I'm going to have my r being 0.01, not 1.01, but 0.01. And that's because when I started writing out, I didn't have a pattern. The pattern was not working the way I wanted it to. So focusing in on just that part, I'm going to write this as 1 plus a negative x raised to the 0.1, and now I'm going to start using how we define the Maclaurin series. So my first term is 1, and then plus, and then it's going to be 0.01 multiplied by negative x, and then it's going to be plus 0.01 multiplied by a negative 0.99, 2 factorial x squared. My third term is going to be 0.01, negative 0.99, negative 1.99, 3 factorial x to the third. And if I were to clean this up algebraically, again, I'm only focusing in on the 1 plus negative x raised to the 0.01. This is going to be equal to 1 minus 0.01x, and then it's going to be a minus again, which is what I needed. And that's going to be 0.01, negative 0.99, over 2 factorial x squared. And the reason it's going to be a negative is because I only have one negative, and this should be a negative x. Just like here should be a negative x. Don't let me drop that negative x. And then it's going to be a negative x because I have a negative and a negative multiplied by a negative 1 raised to the third power is going to be a negative number. So 0.01, 0.99, 1.99, 3 factorial x raised to the third. So I know that that part, which is the 1 plus negative x raised to the 0.01, is going to become, just that part, is going to become the summation of n equals 0 to infinity of negative 1 raised to the n, and then 0.01, choose n, x raised to the n. Now, again, the reason I had to do that is because when I started writing it out, over here, all of this is all kind of messed up. Over here, let me just move that over there. My pattern was not showing up the way that I wanted it to. I didn't have 1 and then all the rest of the terms negative. I had 1, then a negative term, and then all the rest of them were positive. It did not show up the way I wanted it to. So let me go ahead and erase all of this. Erase all of that so that I can actually put the real value in here. So what we did is we rewrote this as 1 minus x raised to the 1, and then 1 plus a negative x raised to the 0.01. Now we know that this part ends up becoming the summation of n equals 0 to 1 of infinity, 0 to infinity of -1, and then it's going to be 0.01, choose n, x raised to the n. Now this is going to be multiplied by 1 minus x. So then what we're going to do is we're going to distribute this through. Go ahead and erase this. So I'm going to distribute this through, and when I distribute it through, what I'm going to get is, this is going to be equal to the summation of n equals 0 to infinity of -1, 0.01, choose n, x to the n. That is the 1 multiplied by that summation. And then I'm going to have minus x, the summation of n equals 0 to infinity. And that should be -1 to the n. -1 to the n, don't drop that. -1 raised to the n, 0.01, choose n, x raised to the n, and that is this distribution. Now I'm going to bring that x back in. So I'm going to take this x and bring it back in. So this is the summation of n equals 0 to infinity of -1 raised to the n, 0.01, choose n, x raised to the n, minus the summation of n equals 0 to infinity of -1 raised to the n, 0.01, choose n, x raised to the n plus 1. Now I could bring this all together as a single summation, and so I have the summation of n equals 0 to infinity of -1, 0.01, choose n, and then in here I would have x to the n minus x to the n plus 1. I would probably leave it like that. I mean, I can get a little fancy, but I'm going to just leave it like that. I could have also left it like this if that was more beneficial to leave it like that, or I could write it like this. So that's it for that one. Let's take a look at these. So let me erase some of this stuff. Let me erase. Okay, so now what we're doing is we're going to use this substitution that's given to us right here to be able to find a Taylor series, and it's going to be centered at a, which is given to us. In this case, a happens to be 0. So this x squared plus 2, the square root is the same thing as 1/2. I'm just going to rewrite this as 2 plus x squared and then raised to the 1/2. The reason I'm going to do that is because that way I can see all the values that I need to pull off here. My b is 2. My x, and I put that in quotes, is x squared. And my r is equal to 1/2. So I'm going to use this substitution to be able to find my binomial theorem. So then this is going to be equal to my b plus a. Remember, a is equal to 0. So the b plus a raised to the r, that's going to be equal to 2 plus 0 raised to the 1/2. My next term, which is 1 plus, actually let me do it like this. I'm going to do it right up above. I'm going to do this as 1 plus x minus a over b plus a raised to the r power. So then this is equal to 1 plus, remember my quote a is x squared, so I'm going to write this as x squared minus 0, because that's what a is, divided by b plus a, which is 2, raised to the r power, so raised to the r power, which our r power happens to be, 1/2. Okay, so then this is the same thing as 2 raised to the 1/2, and then 1 plus x squared divided by 2 raised to the 1/2. Now what I'm going to do is I'm going to use this piece, and I'm going to put that part in into our Maclaurin series definition like we have up here. See, like that. So that is going to be equal to the summation of n equals 0 to infinity of 1/2, because that's my r, choose n, of, and then my x, this is x squared divided by 2 raised to the n. Now don't forget, I still have this 2 raised to the 1/2 out front. So then this is going to be equal to, now I'm just going to rearrange a few things and bring in some of the terms. So the summation of n equals 0 to infinity of, this ends up being x raised to the 2n over 2 to the n. And then when I bring in this number, this 2 raised to the 1/2, this is 2 raised to the 1/2 divided by 2 raised to the n. Now using the rules of exponents, this is 2 raised to the 1/2 minus n. Okay? And I can write it as a single fraction, but I'm just going to leave it like that. So this is going to be 2 raised to the 1/2 minus n, 1/2 choose n, x raised to the 2n. And that's my final answer. This is my final answer. Now let's take a look at my next example here, where I have this 2x minus x squared. Now to be able to use my theorem up above is I need this in the form of some number plus b, and I use, or plus x, I use that x loosely raised to the r. So what I see is I don't have anything for the 2x, and that's the problem, is the x part. Not the 2, but the x part. So what I'm going to do is I'm going to focus in on only the 2x minus x squared. Now, this is the same thing as a negative x squared plus 2x, which is the same thing as a negative x squared minus 2x. Now, I want this to be my, quote, x. And right now, I'm not going to leave it like that because I don't have something raised to a power. I have x squared minus 2x. That is not what I'd like to have. So what I'm going to do then is I'm going to rewrite this as negative x squared minus 2x, and then I'm going to complete the square within there. So I'm going to do plus 1. But I can't just arbitrarily just add 1 without changing the value of what I started out with, which is 2x minus x squared. So the way that I adjust for that, because I'm just adding 1, is I need to think about the fact that if I were distributing this negative 1 back through, this is actually adding, I'm actually subtracting 1. So if I add 1 to it, and if I took off that parentheses and multiplied that negative through, I'd be back to where I started, which is negative x squared plus 2x, or in other words, 2x minus x squared. So 2x minus x squared can be wrote 1 plus, or 1 minus, the x minus 1, the quantity squared. Now, I ignored the square root just so that I can get my algebra straight. I want to get my algebra solid. So where I am now is I'm really looking at the square root of 1 plus a negative x minus 1, the quantity squared. Now I can use that substitution where my a happens to be at 1, my r happens to be 1/2, and my b happens to be 1. So when I write this out using that substitution, I have b plus a. So this is equal to b, which is 1, plus a, which is 1, raised to the 1/2. And then I have 1 plus, and my, quote, x is the negative x minus 1, the quantity squared, minus a, my a happens to be minus 1, over my b, which is 1, plus my a, which is 1. raised to the 1/2. Now, we know that if we were to start writing this out, that we would have a negative sign. We'd have that negative when we were to write it out. So that means this is the summation of n equals 0 to infinity of -1 raised to the n, 1/2 choose n, and my quote x is the x minus 1 raised to the 2n, because it is x, my quote x is really x minus 1, the quantity squared. Therefore, that is where the 2 is, and this is, quote, my x. And this is my final answer. Now, I want to take a look at some of the common functions that can be expressed as Taylor series. So the first one that we have is the reciprocal function that has a transformation, that 1 over 1 minus x can be wrote as the Maclaurin series. This is our interval of convergence. E to the x can be wrote as n equals 0 to infinity of n factorial x raised to the n with this interval convergence, so basically all the time. Sine is defined here, and cosine is defined here, natural log, tangent inverse, and 1 plus x raised to the r, which is what we've just been spending time on. So if we're asked to find the Maclaurin series for each function, I don't have up above any Maclaurin series of 2 raised to the x. I have e to the x, but I don't have 2 to the x. So I'm going to see if I can figure out what it would be with 2 to the x. And so I go back to the way that we first defined Maclaurin series, is that we have our function f of x is going to be equal to f of 0 plus f prime evaluated at 0 over 1 factorial times x plus f double prime of evaluated at 0, 2 factorial x squared. And then this goes all the way up to f of n, the nth derivative, evaluated at 0, n factorial x to the n. So in other words, what I need is some derivatives. I need some derivatives of 2 to the x. Now I'm going to go back to my table of derivatives. I don't remember it, if I don't remember it. And if I have the f of, let me do it this way. If I have d dx and d dx of b raised to the x, this is equal to the natural log of b multiplied by b raised to the x. So f prime of x is going to be the natural log of 2 multiplied by 2 to the x. F double prime of x. Now remember, the natural log of 2 is just a constant, and so I'm really just doing the derivative of 2x. But that gives me a natural log of 2, the quantity squared, 2x. F triple prime of x is equal to the natural log of 2 raised to the 3rd power of 2x. And this continues. I can tell you that f to the 5th, if I wanted to jump to the 5th derivative, this is going to be the natural log. I know you're going to say, wow, that's surprising. The natural log of 5. Natural log of 2 raised to the 5th of 2x. Now, if I'm asked to evaluate all of these derivatives at 0, then what I'm asked to do is f prime of 0. The 0 goes in for the exponent, nowhere else. And so I know that when I put in 0 for the x on that exponent, it's just going to be 1. So f prime of 0 is going to be the natural log of 2. F double prime evaluated at 0 is going to be the natural log of 2, the quantity squared. And if you're thinking, can I jump to the 5th? Yep, let's go to the 5th derivative evaluated at 0. This is going to just be the natural log of 2 raised to the 5th power. So then let's start putting in all that we know. I'm also asked to find the function evaluated at 0. This is 2 raised to the 0, which is 1. Okay, so then I'm going to come back down here, and f of x is equal to f of 0, which is 1. And then it's going to be plus the natural log of 2, 1 factorial x, plus the natural log of 2, the quantity squared, 2 factorial x squared, plus the natural log of 2 raised to the 3rd power, 3 factorial x to the third power, and it continues, which means that this is going to be equal to the summation of n equals 0 to infinity. Now the pattern that I'm seeing here is the natural log. That pattern seems to be going through the entire thing. Remember, I can write 1 as the natural log of 2 raised to the 0. So that was there as well. So this is the natural log of 2 to the 0, 1, 2, 3 on up. Similarly, I know that 0 factorial equals 1. So I know that I can write 1 as the natural log of 2 raised to the 0, 0 factorial, x to the 0, and it's still 1. So what I have then, based on the pattern that I'm seeing, it's going to be equal to, this summation is going to be equal to, and I should put some ... This is going to be equal to the natural log of 2 raised to the n power, x raised to the n divided by n factorial. So that is my final answer. Let's take a look at our next example. So my next example is I am looking at the sine of the square root of x divided by the square root of x. What I'm going to do is I'm just going to focus in on the fact that I have a formula for the sine of x, and we know that this is equal to, from up above, this is one of the ones that we have, the sine of x is equal to the summation of n equals 0 to infinity of -1 raised to the n, x raised to the 2n plus 1 divided by 2n plus 1 factorial. Now this is when I have quote x, and I like to say quote x, so this is quote x. What happens if I have something other than x? Suppose I have the sine of the square root of x. That's my quote x. So then this becomes the summation of n equals 0 to infinity of -1. My x gets replaced with 1/2 raised to the 2n plus 1 divided by 2n plus 1 factorial, which is the same thing as the summation of n equals 0 to infinity. Don't forget that -1 to the n. So -1 raised to the n, x raised to the n plus 1/2 by using the power to power rule. I just multiplied these through, and so I get 1/2 times 2n gives me just n. 1/2 times 1 gives me 1/2. Divided by the 2n plus 1 factorial. And you're like, how come you didn't use that other formula? Why didn't you write all of these shenanigans out? Well, I had to write it out for this one, for my first example, because I don't have any nice little formula up here for a base of being 2. I have a base e, but I sure as heck don't have base 2. So I had to go through the pattern. Now this one, I can do it as sine x. And you're thinking, but what about that square root of x in the denominator? Well, a square root of x is the same thing as 1 divided by the square root of x as a multiplier. So the sine of the square root of x divided by the square root of x is the same thing as 1 over the square root of x multiplied by the sine of x. So that means that this is the same thing as x, 1 over x raised to the 1/2 as a multiplier, which means that this is the same thing as bringing that x in, x raised to the 1/2. Now I'm going to use my power to power, or my rules of exponents. This means this is the summation of n equals 0 to infinity of -1 raised to the n, and then just x raised to the n divided by 2n plus 1 factorial. Again, the reason I was able to do all of this algebra and not have to do the derivatives and try to evaluate it at some value when we're looking at 0 is because I already have a formula for the sine. My formula for the sine of x is this. all I have to do then is see how I can relate that to what's given to me. So I related that by changing the way that I have the 2n. Now, how am I going to do that for the next one? Can I do something like that for the next one? The answer is no, I can't, because, you're thinking why? Well, because I have sine squared. Now, I could write it, if I was inclined, to do this as the summation of n equals 0 to infinity of -1 raised to the n, x raised to the 2n plus 1 divided by 2n plus 1 factorial, and then multiply it by itself, the summation of n equals 0 to infinity of -1 raised to the n, x raised to the 2n plus 1 over the 2n plus 1, like this. And then I can use the Cauchy product like I learned in my previous sections, but yeah, that's a lot more work. And I'm going to try to avoid that if I can. I'm just saying. So what I'm going to do instead is, rather than doing that and using the Cauchy product, I'm going to just use the power reduction formula. We know this is the same thing as 1/2 1 minus the cosine of 2x, which is the same thing as 1/2 minus 1/2 the cosine of 2x. And I'm going to go back to the way that we define it up here in our chart for cosine. Cosine is the summation of n equals 0 to infinity of -1 raised to the n, x in quotes, raised to the 2n over 2n factorial. So let's use that way we define it here to do this. So this is going to be equal to 1/2 minus 1/2. This is the summation of n equals 0 to infinity of -1 raised to the n. My x, my quote x, is 2x. So this is going to be 2x raised to the 2n divided by 2n factorial. Let's go ahead and clean this up. So this is going to be 1/2 minus 1/2 the summation of n equals 0 to infinity of -1 raised to the n of 2 raised to the 2n, x raised to the 2n, over 2n factorial. So then I'm going to go ahead and bring in the 1/2, which gives me the 1/2. I'm not ready to bring the other one in. And then it's going to be minus the summation. Now, this is the same thing as the 1/2, which is 2 raised to the 1, -1. So that means that I can write this part, because the bases are the same. So this is the summation of n equals 0 to infinity of -1 raised to the n, 2 raised to the 2n minus 1, x raised to the 2n, divided by 2n factorial. This needs to be in parentheses. This needs to be in parentheses. This needs to be in parentheses. Okay? Now, I need to be able to bring in that 1/2 somehow. Well, here's the deal. If I put 0 in here, I'm going to get, this is going to be 1. This is going to be -1/2. This is going to be 0, and this is going to be 0. So this is going to give me, if I put in 0, this is going to be 1/2. So if I adjust this to 1, I can bring this in. So I can bring this in by saying this is equal to the -1, the summation of n equals 0 to infinity of -1 raised to the n, 2 2n minus 1, x raised to the 2n, and I wrote x raised to the 2n, let me erase that, 2n divided by 2n factorial. And I can bring that -1 in. So I can go one step further and say this is the same thing as, and I need to adjust because I started at 1 now. 1. This is equal to the summation of n equals 1 to infinity of negative 1 raised to the n plus 1, 2 raised to the 2n minus 1, x raised to the 2n, all divided by 2n factorial. And notice on this one, I was able to avoid doing the derivatives again. Okay, so now let's take a look at this one. Let me erase this. That was from somewhere else. It's just kind of hanging out, I guess. Hanging out, having a good time. Okay. So they're asking me to find, by integrating term by term, they're asking me to find the Maclaurin series. Now, this big F is the fundamental theorem of calculus, is the antiderivative. So it's the antiderivative fundamental theorem of calculus. And this information, if you want to look more, is in the volume 1, and it's of the OpenStax Calculus book, section 5.3. So if you need a refresh on the notation, that's where you're going to find it. Okay, so we're going to start with the inverse tangent. Find the inverse tangent where f of t is equal to 1 over 1 plus t squared, and that's going to be equal to negative 1 raised to the n of 2t. So the first thing I'm going to do is, using the definition of f of x, big F of x, the antiderivative, is the integration from 0 to x of the summation of n equals 0 to infinity of negative 1 raised to the n, t raised to the 2n, and then dt. Now, we know what this is going to be based on our previous integrations that we did, and I think it was 6.2 maybe. But we're going to do it term by term because that's what they're asking us to do. And so we're going to do, this is from 0 to x. I put in 0 into this series. I'm going to get 1 out, and then it's going to be minus t squared, and then it's going to be plus t to the 4th, and then it's going to be minus t to the 6th, and you're kind of seeing the pattern here, dot, 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 dt. When I go to integrate this, this is going to be t, and then it's going to be t to the 3rd power divided by 3, plus t raised to the 5th power divided by 5, minus t raised to the 7th power divided by 7, and evaluated from 0 to x. What we know is that this then becomes x minus x raised to the 3rd power divided by 5 plus x raised to the 5th power divided by, and that should be 3. Excuse me, that should be 3. 3, and then this is 5, and then minus x raised to the 7th divided by 7, and this continues. So we see this is the summation of n equals 0 to infinity of negative 1. I need my first term to be positive, and it is, so I put in 0 into the, if I put in 0 in for n, I get negative 1 to the 0, so that works out. This, if I look at just these exponents, my exponents are 1, 3, 5, and 7. That is the same thing as my denominator. This is an arithmetic sequence, and so my arithmetic sequence would be of the form 2 times my difference plus 1. So that's where the 2n plus 1 comes from, and then divided by 2n plus 1, because that's what my denominator is doing. So my final answer is just going to be this. I should say big F of x is equal to. Now, let's take a look at my next example. I am defining my f of t as sine of t divided by t. And it's telling me this is what is equal to the summation of n equals 0. So doing this, again, term by term, big F of x is going to be equal to the integration from 0 to x. And I'm integrating this thing. To save myself some time and some writing, I'm just going to start putting in n equals 0, n equals 1 equals 2. When I put that in, I get 1 minus t raised to the 3 divided by 3 factorial plus t raised to the 4th divided by 5. Oh, crap. Let's try this again. Let's see if I can make some counting here that makes sense. So it's going to be t squared divided by 3 factorial plus t raised to the 4th divided by 5 factorial minus t raised to the 6th divided by 7 factorial. And this pattern is going to continue dt. This then integrates into t for the first one minus t to the 3rd 3 times 3 factorial plus t to the 4th 5 times 5 factorial minus t to the 7th, should be t to the 5th, t to the 5th, 7 times 7 factorial, and you can see that this is going to continue, evaluated from 0 to x. This then becomes x minus x raised to the 3rd, 3 factorial, plus x raised to the 5th, 5 factorial. And we'll do one more, x raised to the 7th, 7 factorial. So we can see it's alternating again. So I'm going to have, this is going to be equal to the summation of n equals 0 to infinity. And once again, I'm going to pay attention to my powers. I go 1, 3, 5, 7. And so I'm going up by powers of 2. So I have a difference of 2 each time. So I still have the alternating, so negative 1 raised to the n, x raised to the 2n plus 1. My denominator has the 2n plus 1 factorial, 2n plus 1 factorial. At the same time, it has the 2n plus 1. Because this is my 2n, and this is my 2n plus 1 factorial. So my final answer is big F of x is equal to, and that is my final answer. On these examples, they're asking us to find our first 3 non-zero terms of the Maclaurin series. And we're tempted to write this as the sine of x divided by the cosine of x, and then use those definitions of sine and cosine from up above. The way that we define it in our box up here, our definitions up here. So we're tempted to do that. Now, I want to caution you about doing that. It's in and of itself is okay, but what you're going to end up with, if you do it like that, you don't get to do it necessarily term by term. What you're going to get is, if you were to expand this out using the definition of sine and cosine, is you're going to get something that looks like this. You're going to get 1 over 1 factorial x for the sine, and then minus 1 over 3 factorial x cubed, and it's going to continue. And then you're going to be dividing by 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, and etc. Which is going to be kind of a bear to try to simplify, right? This is not going to be very easy to simplify. So what I'm going to do instead, because I'm really tempted to use the way that we define them up above, but what I'm going to do is I'm going to do it by the derivatives. It's going to be, I don't know, I think it's 6 and 1/2 a dozen of another. At least writing it out initially before you simplify by writing it as sine over cosine is probably going to be easier out of the gate. But what I'm going to do instead is just do some derivatives, the way that we define it by derivatives. So the first thing I need to know is f of 0. So the tangent of 0, which is equal to 0. Now let's start doing some derivatives. The derivative f prime of x is going to be the absolute value of the secant squared of x But, you know, something squared is just going to give us just that. And so if I then evaluate it at 0, the secant of 0 is equal to 1. Then I'm going to look at my next one, my second derivative. So my second derivative is going to be the derivative of secant, which is 2 the secant of x. And then the derivative of secant is secant x tangent x. Tangent x. And if we evaluate that at 0, so f double prime of 0 is going to give me, for the second derivative, is going to give me 0. Now remember, I need to find 3 non-zero, so I have to keep going. My third derivative of x, and I'm just going to give you what the third derivative of x is without doing the work for it. It's just going to be 4 secant x tangent squared x plus 2 the secant raised to the fourth x. Now that is my third derivative. When I evaluate my third derivative at 0, this is just going to give me 2 because this is going to go to 0, and then I'm just doing the secant of 0, which is 1, raised to the fourth power, still 1, which is 2. I'll go ahead and do my fourth derivative, and again, I'm just going to give you the answer. I'm not going to show you how I got it. I'm just going to give the answer because we're not doing derivatives here. We have the secant for the secant of x, the tangent of x, and then this is going to be multiplied by the tangent squared of x plus, actually, let me write it this way. Indecision, it's interesting. So we have 4, this is going to be 4 the secant of x, tangent to the third x, plus 8 the secant to the third x, tangent x, plus 8 the secant to the fourth x, the tangent of x. Now what I see is every single one of these lovely terms have got a tangent. So the fourth derivative evaluated at 0, the fourth derivative evaluated at 0 is going to be 0. So I have to find the fifth derivative because I've got my first term, my second term, and I need 3 of these lovelies. So let's do my fourth derivative, my fifth derivative, boom. Fifth derivative of x. Again, I'm just going to give you the answer. 4 the secant of x, tangent to the fourth x, plus 32 secant to the fourth x, tangent squared x, plus 36 secant to the third x, tangent to the x, plus 8 secant to the sixth x. Ooh, nice. I now know I'm going to have at least 1 secant to the fifth x. That when I evaluate it, the fifth derivative evaluated at 0, everything that has got a secant will go to, or a tangent will go to 0. So I end up with just 8 plus 8, which is 16. And I finally have another term, my third term, in fact, that does not go to 0. So where am I? Well, I'm in the land of derivatives, and it was like the best we've ever had. My tangent of x is equal to f of 0 plus f prime of 0, 1 factorial x plus dot, 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 dot. Now, the ones that don't go to 0 is my first derivative, my third derivative, and my fifth derivative. Everything else is going to go to 0. So this is going to be equal to x, because that's the one that's associated to my first derivative. That doesn't go to 0. Plus 2 over 3 factorial x raised to the 3. Plus 16 over 5 factorial x raised to the 5th plus dot, dot, dot. So let's just clean this up a little bit. This is x plus 2 over 3 factorial is 2 over 6, which gives me, what does that give me? 1/3. So 1/3 x raised to the third plus 16. 5 factorial is 120, so I have 16 over 120. This reduces to 2 over 15 x raised to the fifth plus dot, dot, dot. So there it is in all of its glory. Let's take a look at our next example and pray that it isn't as much fun as what we just did. We have f of x is equal to e to the x cosine x. So with this, what I'm going to do is I am going to do the easiest, least path of resistance. And I know that e to the x, as defined above, is going to be the summation of, as n equals 0 to infinity, of x raised to the n, x raised to the n over n factorial. So I'm going to start writing these lovelies out. My first one is 1 plus 1 over 1 factorial x raised to the 1 plus 1 over 2 factorial x raised to the 2 plus 1 over 3 factorial x raised to the third plus dot, 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 dot. I'm going to do the same thing for cosine. So the cosine of x is the summation of n equals 0 to infinity of -1 raised to the n, and then it's going to be x raised to the 2n over 2n factorial. So let's start writing these out. So I write these out, and the first one is going to be 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth. And let's just do wild and crazy one more. Minus 1 over 6 factorial x raised to the sixth. Now, so let me make sure that's right. So I have 2, so 2, 4, and then I'm on my third, 2, 6, okay. Now, what I basically have then is this 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third plus dot, 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 multiplied by 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. And then I'm going to start multiplying these. So I'd multiply this one by each one of those terms. So I'm going to distribute this through. And when I distribute this through and clean up, and you can verify this on your own, that this ends up becoming 1 plus x minus x raised to the third divided by 3, divided by 3 minus x raised to the fourth divided by 6, and then it's going to continue, dot, 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 dot. So this is what it's equal to. I only needed to find the first 3 terms, so I only needed, well, that's more than I need, but that is what e to the x cosine of x is equal to. I didn't have to do a lot on this one. I could have done it by derivatives. Sure. If the derivatives are easier for you, absolutely do it by derivatives. This one up above the tangent, I pretty much had to do it by derivatives. This one, I did it by first the definition, and then I just distribute it through and combine up like terms. So there you have it. On these last couple of examples, and I only have 2 more examples to do, and then this is done, because we're just going to talk a little bit about the final word. So let's just look at these last 2 examples. We want to find the radius of convergence for each one of these series. I have the natural log of 1 plus x. So the first thing I'm going to do is, I know that this is defined by, because it's by definition up above. This is going to be equal to the summation of n equals 1 to infinity of -1 raised to the n, this is the definition up above, of n plus 1, and then it's going to be x raised to the n over n. To find my radius of convergence, I use back what we learned, the limit, the ratio, as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n, which is equal to the limit as n goes to infinity of the absolute value of negative 1 raised to the n plus 2, because this is my n plus 1, x raised to the n plus 1 over n plus 1 multiplied by n over negative 1 raised to the n plus 1, and then x raised to the n. Now, what we know, because we're doing the absolute value, is that we can pretty much ignore those pieces. So then what I really have is this is equal to the limit as n goes to infinity of x raised to the 1 by the rules of exponents. I'm going to take this and this by the rules of exponents. That just becomes x raised to the 1 multiplied by n divided by n plus 1, absolute value. So this is the absolute value of x, the limit as n goes to infinity of the absolute value of n over n plus 1. And of course, we can take a L'Hopital's and do the derivative to find the limit, which just gives me the absolute value of x. And this is rho, and this has to be less than 1. That tells me my radius of convergence is 1. Boom. So that's kind of cool. Kind of nice to make that connection from previous work to this. It's kind of nice. All right, so let's look at the sine, the hyperbolic sine, and I pray that I've got the hyperbolic sine up above. And so I'm going to go look to see if I have the hyperbolic sine up above. And I don't directly, but what I know is that I can do this by doing e to the x. So I'm going to rewrite this as 1/2 e to the x minus e raised to the negative x, and I have a rule for e to the x from up above. So this is going to be equal to 1/2 the summation of n is equal to 0 to infinity of x raised to the n over n, and then the minus the summation of n equals 0 to infinity. Now, the fact that I have this negative x, then this is going to be x raised to the n divided by, and I have n factorial, and this is n factorial too. Helps if I pay attention. But because my x is really a, quote, negative x, I do have to make that adjustment by raising it negative 1. Let's kind of clean this up just a little bit. I know that I can bring this negative 1 in by writing this as 1/2 the summation of n equals 0 to infinity, x raised to the n factorial. And then it's going to be plus the summation of n equals 0 to infinity, x raised to the n negative 1 raised to the n plus 1 over n factorial. Which means now I can write this as 1/2 the summation of n equals 0 to infinity. Because of the fact that my indices are the same, I can bring this in as x raised to the n factorial plus x raised to the n negative 1 raised to the n plus 1 divided by n factorial, which is equal to 1/2 the summation of n equals 0 to infinity of 1 plus, I have negative 1 raised to the n plus 1, and then I have x raised to the n factorial, because I'm able to factor that out. Now remember, my eye on the prize is I'm trying to find the radius of convergence. And right now, if I were to try to do the radius of convergence by doing the ratio theorem, the limit as n approaches infinity of a sub n plus 1 divided by a sub n, my problem child is this. So I'm going to see if I can clean this up a little bit. So I'm going to start writing out my terms and see if I end up with a, quote, new series that will make my life a little bit easier. So I have 1/2, and it's going to be multiplied by. I put in 0, and I'm going to get 0 out because of my problem child right here. I put in 0 right there. -1 to the 0 plus 1 is going to be -1 to the 1. So -1 times, or -1 plus 1 gives me the 0. So that's why that gives me 0 for the first term. I put in a 1 into my next term, and I'm going to get plus, and it'll be x, and then n factorial, and then I have a 2, because 1 plus 1 is 2, -1 squared gives me 1, so 1 plus 1 is 2. Cool. And then I do x squared over 2 factorial, but that gives me 0. Okay. I'll do my next one, x to the 3rd multiplied by 2 divided by 3 factorial. And you can see, if you continue on this, this will continue plus ... So this is the same thing as 1/2 x multiplied by 2 over 1 factorial plus x cubed multiplied by 2 over 3 factorial. And I can guarantee the next one would have been x raised to the 5th multiplied by 2 multiplied by 5 divided by 5 factorial. When I distribute this 1/2 through, I'm going to get x over 1 factorial. I'm going to get plus x cubed over 3 factorial. There should be 1 right there. Plus x raised to the 5th over 5 factorial, which I can write this now as the summation of n equals 0 to infinity of, now notice I don't have to worry about the -1 to raise to any power anymore. So I'm going to have x raised to the 2n plus 1, and then over 2n plus 1 factorial, which, if I now have to do my radius of convergence, because I think that's what I was doing. Am I just still doing it? Yes. So as I do my radius of convergence, I'm going to do the limit as n approaches infinity of the absolute value of x raised to the 2n plus 2 over 2n plus, and I need to add one more, so 2 factorial over, and then I'm going to have, it's going to be reflected over, so it's going to be 2n plus 1 factorial over x raised to the 2n plus 1. And we know how to do those. So you find your radius of convergence that way. But notice how I actually had to write out some of the terms, because trying to find the radius of convergence by using the ratio test on that problem child piece would be difficult. So if you're finding that trying to use the ratio in theorem may be beneficial for you to write out some of the terms to see if it is going to be able to be rewrote as a much easier series. Now, final last words. We learn the Taylor and Maclaurin series because it allows us to evaluate non-elementary integrals. So integrals such as the antiderivatives cannot be wrote as elementary functions, which are difficult to do. So like the cosine of the square root of x, or e raised to the negative x squared. Those are difficult to do. And we can do it by approximation. We don't ask for you to have the software for this class. We probably will for the next one. I think require you guys all to at least learn the software so that you can see how powerful the software is to be able to find these integrations. And we also use them to approximate differential equations. So there's a lot of uses for them. This is all we're going to say. This is the end of the Taylor-Maclaurin series, our power functions for now. We're going to put this to bed for now, and we will see you in parametric equations next.